All right, we get to start derivatives. Now it kind of is going to start to feel like we're in calculus class a little bit, but of course, because this is real analysis, we're going to kick everything up a notch and focus on proofs and kind of why things work the way they do. But we'll do a few calculus problems here and there, and I hope that you all enjoy that. Okay, so for differentiability, the first thing I want to note is that when we hit this section from now on, we're going to let you do limits of sequences and limits of functions. We're going to use limit laws to do the limits. So for example, if I asked you, what is the limit as x goes to infinity of x cubed plus x squared plus 1 over 3x cubed minus 5. You could do all sorts of different things, but the answer is that's 1/3. And at this point, I'm okay if you're just saying by limit laws, that limit equals 1/3. Don't feel like you have to go through all the details and stuff, and you can just say by limit laws. I want you to know how to do those limits, but at the same time, we don't want to spend every waking moment bounding limits by epsilons. So we're going to kind of let that stuff fade into the background. I know that we could if we ever really wanted. Okay. So what about derivatives? We remember derivatives from long ago, from calculus class, and all a derivative really is just, we're trying to measure the slope of the function at some point. So here's our point, and here's our tangent line, and we're trying to measure the slope of that tangent line. And hopefully this is something you all are quite familiar with. This point is the point A. And then what we're going to do is we move over a little bit, and we call this A plus H, right? And so we move over to A plus H, and that gives us a second value here, which is close to the value in our function. And then the value of the function is f of A and f of A plus H. And so this gives us our limit definition. So we see that the slope is f of A plus H minus f of A over A plus H minus A. And so that becomes f of A plus H minus f of A over H. And this is the formula that we all remember from calculus class. It was everyone's favorite part of calculus class. And then what do we finally do? Finally, with the limit as h approaches 0, that makes this point get closer to that point and makes this tangent line become closer and closer to the actual tangent line. So instead of doing that secant line, which is the slope of this thing, we get a point right here, which is giving us this secant line, which is closer. Okay, wow, this is all awful looking. My graphs didn't work out really well. But hopefully we all remember a little bit of derivative. I just wanted to remind you, for those of you who it's been a while since you've been around or in calculus. So what is the definition of the derivative? Well, we're going to say the definition of derivative at a point is just the limit as h approaches 0 of f of A plus H minus f of A over H. And now that we know what limits are, we know if this exists or not. And so if this limit exists, then we say it has a derivative. If it doesn't exist, then we say it doesn't have a derivative. And even though I told you could use limit laws, there's going to be times where we still want to tackle this thing using either epsilons or sequences or something like that. So don't just throw all those things out of your mind. Keep them in the front of your mind. There's also another definition, which is equivalent, that you are probably familiar of. It's the limit as x approaches A of f of x minus f of A over x minus a. And these are equivalent definitions, and I'm sure you all have seen this. But what I want to do now is introduce you to a couple definitions that are not intuitively the same as that definition, but they actually are the same. So one definition, the first one that the book uses, says f is differentiable if there exists a function capital F of x such that little f of x, oh, maybe I should write up here, we should write what we're trying to do, f of x is differentiable if, and then if there exists a capital F of x such that little f of x equals capital F of x times x minus a plus f of a. And so this is, and this f of x and this f is continuous. So this is one way to define the derivative, and this is actually going to be really useful because this takes our division, and we all know division can be sticky, especially when we're worried about dividing by 0, and turns it into multiplication. So multiplication is a lot nicer to work with. But if you look at this really closely, if you unpack this and solve for f, our capital F is just f of x minus f of a over x minus a. And so it turns out that the capital F is what we're calling our derivative function. All right. So this was one way that the book went about defining derivative. I encourage you to go look and kind of read that, the book. A second way that the book defined what a derivative was, they said a function is differentiable if and only if there exists a t function. They used an h. I'm going to use, or I used an x. I'm going to use an h equal to m times h, such that our function f of x equals the limit. Oh, sorry, not f of x. Such that the limit as h goes to 0 of f of a plus h minus f of a minus t of h all divided by h equals 0. So it's differentiable if you can find a function that makes this limit become 0. And if you look really closely at this, what you'll notice is that this function, the m is suggestive that m is that f prime of a function. Again, check it out for the book, but what you'll notice is a couple things. So if you put m times h in here, then and then split it up, then you'll notice you get your derivative minus m. So if we take this as it is, and then replace that with the m times h that we see here, then you notice that you could split this up into two fractions. One fraction is your difference equation, and the other fraction is m. And so you see that m is defined to be the derivative. And then the other direction, if we leave this as t of h and solve for it, then you'll notice that t of h is the derivative equation. So, okay, so the m in the t of h is the derivative equation. Okay, so these are just other ways to define the derivative. They're not things we're going to use a lot, but there'll be times in certain definitions and certain formulas that these are better for proving things than others. And actually, right now, we're going to go ahead and do one of them. So one of the first things we're going to do is we're going to use this formula to tackle a proof that can be a little bit sticky if you try to do it in a calculus 1 way. So we have all of our derivative rules. We have our product rule, our sum rule, right? So we have our sum rule, our product rule, our quotient rule, and all those. The one I'm going to focus on is the chain rule, and it's the one that's the least obvious for us, right? So let's look at the chain rule. And basically what the chain rule says is that if f and g are functions, and I'll let you look in the book. I don't want to write down right now all of the things that go into the definition, but f and g have to be differentiable at these different points. I guess I can write it. So f is differentiable at a, and g is differentiable at f of a, at the point f of a, which maybe I'll call that b or something. Then you all remember what the chain rule says. It says that if I take the derivative, and I'll write this notation, of g of f of x, evaluated at x at a, is equal to, here we'll put evaluated at x equals a, is equal to g prime of f of a times f prime of a. Okay, so this is the formula that you all kind of remember somewhere along the way. And if you start trying to prove this, you run into a little sticky issue. So I proved this in my calculus class, but I kind of cheat when I do it. And the way I prove it is I go, hey, this function, the limit as h approaches 0 of g of f of x minus g of f of a divided by x minus a. Well, what I'm going to do is I will multiply this by f of x minus f of a divided by f of x minus f of a. And then you see I can now rearrange all of this stuff and get g of f of x minus g of f of a divided by f of x minus f of a times f of x minus f of a over x minus a. Okay, so this looks like a decent proof, and if you're a Calc 1 student, you go, oh, that's great. Because now, if I look at these things, maybe I'll erase all these, and so now if I look at this final result, I can see that this piece right here is simply g prime of f of a, because it's the derivative equation with f of x taking the place of x. And then this thing right here is f prime of a, because this is our derivative equation for a. If you're a Calc 1 student, you're like, okay, that's good. Or probably you're not paying attention, you're just ready to get done with the section, and you know I'm not going to ask you to prove this. Okay, but if you're an analysis student, you should look at this and be a little bit concerned. And the reason we should be a little bit concerned is this. The reason we should be a little bit concerned, at least from my opinion, is this term over here on the left. This piece, this is not exactly the definition, right? Because this in the bottom is not. This is not x minus a. Now, it's true that is becoming small just at the same time that x minus a is becoming small. But it is definitely not the same thing as x minus a. And what's even worse is this piece right here could equal 0, right? So there's no rule that says f of x can't hit f of a. We can let f of x hit f of a time and time again. And so there's no rule that they can't equal each other. And so if that was 0, then I would have a bunch of points in this limit that don't exist. And and in fact, I could have points that don't exist, an infinite number of them. I could have them, discontinuities to this function that lead all the way right up until the point, oh, sorry. Notice I messed this up all the way. This is x approaches a. All the way up until x equals a. I could have lots of these. So I'm not going to use this proof. Instead, I'm going to use that definition that we had on the last page, that first one that felt a little strange. Kind of this definition where we're thinking of a derivative in some way as a slope. So notice this kind of looks like a linear equation, right? But it's a continuous function times x minus a plus f of a. Some people will call this the linearization equation or the linearized equation or something. But okay, let's try to do that proof as we go. Let's try to do a proof using that. Okay, so what I'm going to notice is I'm going to notice two things. Since f is differentiable, and here let me erase all this so we don't have to look at it. Okay, since f is differentiable, there exists some function. I'm going to call it f prime of x, such that so I'll just say f prime. There exists an f prime of a. Let me erase this. There exists an f prime of a such that f of x equals f prime of a times x minus a plus f of a. And all this f prime is this is just the equation from this function right here that we had. Okay? Okay, so similarly, I'll have that there exists a g prime of a such that, let's do b instead of a, and I'm going to let b equal f of a, such that g of x equals g prime of b times x minus b plus f of b. So now we have, no, plus g of b. Sorry, that last one's a g. Okay, so all I've done is write down the definitions based on that kind of linearized equation that we had earlier. But now that I have these two equations, I can put them together. I can say, what is g of f of x? Well, simply put, g of f of x is just what we get when we take the f of x equation and stick it into the g of x equation. So that means we've got g prime of b times, and now instead of x, we have f prime of a, x minus a plus f of a, minus b plus g of b. And so if you see here, what you see is that all I did was I just took this equation and plugged it in for x, because that's exactly what we do when we substitute. Okay, so here we go. So that means this piece over here becomes. So that means this piece down here. And notice that f of a equals b. So that means f of a minus b is now equal to 0. And then we'll also so that means that piece equals 0. And then I'll do a little bit more work as we come through here. So that means this part, g of f of x, is now equal to g prime, let's replace the b with an f of a, times f prime of a times x minus a plus g of f of a. And what you notice is now I fit that definition again, except now I fit that definition with my g prime equation, and you'll see that I have my derivative setting right here. So that means that this expression, which is my chain rule expression, is the derivative of my chain rule function. Okay, so this is one way to go about proving the chain rule, and it's nice because we don't have to worry about all those issues of dividing by 0 or is the denominator what we want to be. Instead, we take the functions, write them out in their linearized form, and then add them together. Okay, I'll let you tonight prove the other ones, and you can prove these rules using the traditional derivative formula. So remember the sum rule, that's if we have f plus g and we take the derivative of it, it's the same as taking the derivatives of their pieces. The product rule, you all remember the product rule. It's the derivative of the first times the second plus the first times the derivative of the second. And then finally, everyone's favorite calculus rule. In fact, you ask students, do you know the fundamental theorem of calculus? And they'll say, yeah, I know that. I've got everything that I could ever want to know from calculus because I know the derivative of x to the n is n x to the n minus 1. Hint, that's not all there is to calculus. But okay, prove those three things for us, and we'll kind of let you show that off tomorrow when you come to class. All right, so now it's time to start talking about some theorems. And so this first section, we're really only going to do a couple theorems that have to do with derivatives, and particularly kind of relating to this formula, this linearization formula that we have. They're not relating, but they kind of look the same in some ways. So the first one is called Rolle's theorem. Some of you may have learned Rolle's theorem. I never did. I learned the mean value theorem that we're going to talk about in a second. And Rolle's theorem is really just a special case of that. But it's easier to prove. So we're going to prove Rolle's theorem and then use Rolle's theorem to prove the mean value theorem. What does Rolle's theorem say? It says if f is continuous and differentiable, so continuous on this closed interval and differentiable on the smaller interior interval. By the way, if it's differentiable on the closed interval, then it would also be differentiable on the closed interval. we've just loosened the, requirements as much as we possibly can. So it can just be, so it can be just differentiable on the inside and then have those outside edges be continuous. If f is continuous on a closed interval and differentiable on an open interval, and f of a equals f of b. So let's think, so what does this look like in a graph? This means we've got a and b here, and that means that this point, f of a, is equal to this point, f of b. Well, if it's closed and differentiable, then that means our graph has to do something like this, right? Or it could do something like this. Or it could do something like this. Okay, so as it does these things, what we're going to claim is that there's some point on here that has a slope of 0. Because if you kind of look through, those 2 points are flat. So if you go up, then you have to come back down, and you have to have some point that has a slope of 0. And then your calculus mind, this seems intuitive because of course you'll have a maximum or minimum in there. Okay, so let's clear the page and we'll start over. So let's do our proof. So we will assume that f is not constant. So assume f is not constant. And if it's not constant, then what we know is that there must be, the maxes and minimums must occur somewhere in the interval. And we know that it's going to have either a max or a min. So let's just assume it's a maximum. And so we'll just say, and there exists a maximum value by the extreme value theorem. And we'll let that maximum value, we'll call it m, and we'll assume that okay, sorry, I'm blubbering about. So we know there has to exist a maximum value, m, and by the extreme value theorem, m is actually some point in our space. There exists a c in a and b such that f of c equals that maximum value. Okay, so that's great. Notice there actually, this problem could have been minimum. I could have done, there actually doesn't have to be a maximum value. There could be a minimum value. We, in the math world, like to call a proof like this a proof without loss of generality. And what we mean by without loss of generality means the rest of the proof proceeds the exact same no matter which choice you made here. And in this case, the proof, if the function had a minimum but not a maximum, it would proceed the same, but our inequalities would be turned the opposite direction. Okay, so let's go about seeing if we can prove the rest of this. Well, what we know is because it's a maximum, we know that f of c plus h minus f of c must be less than or equal to 0 for all h values, such that c plus h is still in our interval AB. Now, why is this? Well, this is because our m is a maximum. So and f of c is the maximum value. So in other words, if you're at a maximum value and you take a value different than it, then you have to be less than that. And now if you subtract those values, then you have to get something less than 0. This is because every x has to be less than f of c. So then if you subtract that f of c over, you get something that's necessarily less than 0. Okay? That's what maximum means. Okay, so now what I'm going to do is I'm just going to write out the limit as h approaches 0 of f of c plus h minus f of c all over h. And what we'll notice, the limit from the right, and what we'll notice if we take the limit from the right, then our top part here is greater than or equal to 0, but h is also greater than or equal to 0. So that means that this limit must be greater than or equal to 0. But also, let's take the limit from the left. So if I take the limit from the left, then what you'll notice is now the top is greater than or equal to 0. And now, because I'm going from the left, my h is made up of negative values. So that means this thing is less than or equal to 0. But now I have the important result. If my limit exists, and because it's differentiable, it means this limit exists. Because it's differentiable, these two limits, I guess I could write this. I don't have to be that lazy, do I? Okay, because it's differentiable, the limit as h approaches 0 from the right of that f of c plus h minus f of c over h has to equal the limit as h approaches 0 from the left of f of c plus h minus f of c over h, because that's what it means to be differentiable. It means the limit exists, and so the left-hand limit and the right-hand limit have to equal each other. But how many numbers out there are there that are both greater than 0 and less than 0? There's only one, and that number is 0, and that proves our theorem. Okay, so that's how Rolle's theorem works, and it's a really nice result, and it's really valuable in itself. So there's a lot of times we use Rolle's theorem. Often we use Rolle's theorems to show that we have a derivative 0 somewhere in our graph, and it ends up being nice sometimes. All right. But now we have something like the mean value theorem. The mean value theorem ends up being super helpful. And let's just talk a little bit about the mean value theorem. We're using the same assumptions as we did with Rolle's theorem, but this time we're going to let f of a and f of b be different values. So f of a can be here, and f of b can be here, and we have that value, and then our graph, looks something like that. Well, if you remember the mean value theorem, it is that we have f of b minus f of a equals f prime of c. So it means that there exists a c such that this equation is true. Notice Rolle's theorem is just a special case where a and b are, f of a and f of b are equal to each other, so we get 0 over here on the left. If you look this up in your calculus textbook, it probably writes this as f prime of c equals f of b minus f of a over b minus a. And this is another perfectly valid way of writing the mean value theorem. And if you look, you'll notice what this is. This is the derivative, and this is the average rate of change from way back when. So that means that if I take my average rate of change, which is the slope of that line, there's some other point on the graph that has a slope that's parallel to it. So so what I can do is I can always find a c value that has a slope parallel to the slope that I would get from going straight from a to b. And that's kind of what the mean value theorem tells us. It turns out the mean value theorem is really useful, and it's useful in a lot of different ways. One reason that it might be useful is if you know something about the function, if you know about starting and ending values of the function, then you can find a derivative to meet your needs. We will do this when we talk about integrals. We'll divide our interval into small pieces, and then we'll find we'll split our interval up into little pieces, and then we will pick our sample points, specially using the mean value theorem. But often, as you'll see in some of the homework in this chapter, what we're also going to do is go backwards, and that is if you know something about the derivative, that is, if we know the derivative is positive or the derivative is negative, then we'll use that to learn about the endpoints, to learn the endpoints either have to be bigger or smaller than the derivative value. Okay, so let's get to proving this thing, because that's what we really want to do. And proving this thing is actually quite simple, because all we have to do is use Rolle's theorem. We just have to use it with the right function. And so I'm going to let the function g of x be f of x minus f of a minus f of b minus f of a over b minus a times x minus a. Okay, now this is just a function, but this function is obviously a differentiable because f of x is differentiable. F of a is a constant. This f of b minus f of a is a constant, and x minus a has a derivative. And so we've just put together a bunch of things that have a derivative. So this is obviously a differentiable and continuous. So that means we can now start tackling the problem. And the first thing we'll notice is that g of a, what happens if I put an a in this equation? Well, notice I get f of a minus f of a. So these two pieces cancel each other out to give 0. And then minus, and then I've got this difference quotient times a minus a. So that those a's cancel each other to get each other 0. So that is just 0 all by itself. Okay. Similarly, if I take g of b, what am I going to get? I'm going to get f of b minus f of a minus f of b minus f of a over b minus a times b minus a. But you'll see that this b minus a and this b minus a cancel each other out. And then we've got f of b minus f of a minus f of b minus f of a. So that ends up being 0 also. So Rolle's theorem says that there must exist a c such that g prime of c equals to 0. So we found 2 points that are both have the same value. In fact, their value is 0. So there must be some point in the middle of Rolle's theorem that has a 0 value. So let's go find it. So notice at that point, g prime of c, well, first, g prime of x, we can calculate it. G prime of x is f prime of x. The derivative of constant is a 0, and the derivative of this is minus f of b minus f of a over b minus a times, and the derivative of x minus a is just 1. So if I put c inside of here, I get g prime of c is f prime of c minus f of b minus f of a over b minus a. And that is supposed to be 0. I do a little bit of algebra with this. So you enjoy your algebra. What are we going to do? We're going to move this expression over to the other side, multiply back by b minus a, and you get f prime of c times b minus a equals f of b minus f of a. And that's our mean value theorem, just as we wanted it. All right. We also have a generalized version of the mean value theorem. The mean value theorem is really useful for telling us relationships between the function f and its derivative. So if you want to make a connection between the values of f and its derivative, the mean value theorem is often the place to go. The generalized mean value theorem tells us about two functions. It tells us about a function g and a function f, and these are the same assumptions. Both g and f have to meet the same assumptions. Okay, so and you don't want the g of b and g of a to equal. I mean, I guess if they equal, the theorem's still true. It's just not very interesting. Okay, so the generalized mean value theorem is usually really handy for giving us relationships between the derivatives of two functions. So if I know something about f and g, I can also know something about f prime and g prime and how they relate to each other. You prove this very much the same way as you do the mean value theorem. You just use a little bit more complicated equation here. But you take the derivative of it, use Rolle's theorem to show that you have a 0, take the equation of that, set it equal to 0, and you get this equation. I spent a little time asking myself, well, what does the generalized mean theorem mean? And there's one nice way of visualizing it and kind of thinking about what this is actually telling us geometrically. And I want to share that with you just for a minute. And that is, if you remember back from Calc 3 and other courses, you studied parametric curves. You may have even done it in Calc 2. And when you have parametric curves, you define x and y explicitly. And so we might think of defining x as like our f of x function and our y as our g of x function. And if that's the case, what we would get is we would get some function, that kind of moves around moves around in space somewhere. Well, what this equation is telling us is that this term, by the way, I can take that equation and rewrite it as f prime of c divided by g prime of c. Let's tell you what, let's do it the other way around. Let's put the g's on top. G prime of c over f prime of c is equal to g of b minus g of a over f of b minus f of a. All I did is move both the derivatives on the same side and everything to the other side. But what you'll see this is, if I look at this part on the right, I've got a change in f, which is a change in my x values. So that would be like this distance right here. And then if I look at the top, you'll notice I have a change in y, which is like a change in my y values. That's like that distance right here. And so what is this expression on the right telling me? This expression on the right is really just giving me the slope through the starting and ending point of this parametric curve. Well, okay. Well, then what is g prime of c over f prime of c telling me? Well, g prime of c is like a rate of change in the y direction, and f prime of c is a rate of change in the x direction. So what it really is it's some point on here that has a derivative that the two slopes match up. So what we're saying is similar to we talked about the mean value theorem. This theorem has two lines that are parallel to each other. They have the same slope. It's just kind of in a parametric way. So that's kind of a nice geometric understanding of why this theorem is called the mean value theorem and how it's related to the other ones. But it's really great for connecting f's and g's together. Okay, let's end this conversation with a nice little proof. This proof should go fairly well. But all it says is that if f prime of x is greater than or equal to 0 for all x, then f is increasing. You might be sitting there going, well, of course this is right. This is what we say in calculus. In fact, we define increasing using f prime of x is greater than or equal to 0. But we don't want to do that. We want to define increasing. Sorry, I'm struggling. We define increasing as, if x1 is less than x2, then f of x1 is less than f of x2, less than or equal to. All right, so that's what increasing means. It means that if your x values get larger, your y values get larger also. But why should that be the same as the derivative being greater than or equal to 0? Well, here's why. What we have to do is we just have to let x1 and x2 be in our interval. So we'll start by saying let two values be in our interval. And tell you what, let me just make sure one's smaller than the other. So we'll let x1 be less than x2, and they will both be in our interval I. Well, the mean value theorem that we did just a second ago gives us a relationship between those two values. It says that there exists a c in the interval such that f prime of c times x2 minus x1 equals f of x2 minus f of x1. Well, what you see at this point is that f prime of c, this is greater than or equal to 0 by our assumption that we assumed f prime of x is greater than or equal to 0. I guess I should have written my assumes down here, but I was being lazy. And then this is greater than, actually strictly greater than or 0 because we picked the point where x2 is to the right of x1. So that's greater than 0. Well, what happens when you multiply two things that are greater than 0? You get something else that's greater than or equal to 0. So therefore, f of x2 minus f of x1 is greater than or equal to 0, which is the exact same thing as saying f of x2 is greater than or equal to f of x1. And that's what it means to increase. We started with 2 points. We started with 2 points where x1 was less than x2, and we ended up with f of x1 being less than f of x2. An interesting result here is that, well, what if the derivative is equal to 0 for all points? So what if we had f of x is equal to 0 for all points? Well, then f is a function that is both increasing and decreasing on your interval, right? So it's increasing because the greater than or equal to 0 proof shows that it's increasing. It's decreasing because the less than or equal to 0 proof shows it's decreasing. But what functions are increasing and decreasing at the same time? The answer is constant functions. So f prime of x equals 0 for all x in the interval only when f of x is a constant function. And then one nice result that the book points out is that if you have two functions who, when you subtract them from each other, f prime of x minus g prime of x equals 0 implies that f of x minus g of x is equal to a constant for all x in your interval. These may seem trivial, but actually there's a lot of times that it's maybe easier to show that a derivative is 0 than it is to show that something is constant itself. All right, well, thank you for taking the time to listen. I'll have one more video tomorrow. We'll do some of the kind of big theorems. We'll do like L'Hopital's rule and some things like that. So look forward to that.